Hello, everybody, and welcome to this special session of Amberg TSP Webinars. We would like to thank the TSP user community, our distribution partners, and special guests for participating in this session. Today, we are very excited since we are announcing worldwide the launch of the next generation of the TSP technology. Therefore, in this session, you, as the TSP community, will see exclusively for the very first time the new hardware components and software of the TSP of tomorrow. So do not wait any longer, and let's start with this special session. As usual, let's have a look to the webinar taskbar. If you want to open the attendees panel, you can click on the red arrow button. Please check your speaker settings and change it in case you cannot hear us clearly. In the chat panel, you can enter your questions during the webinar. We will collect them and answer via email. My name is Joseph H. Mendez, and together with my colleague Thomas Tickman, we are going to present this seminar. Very glad to see all of you. So then let's start with the contents of the webinar. Today, so first we are going to take you in a travel through a working site in Switzerland, and then we will go and present the new components, the hardware components, and also the software of the new TSP wireless and TSP Impact. So let's join me in a travel now in Switzerland.
Good day to you all. I'm sending you today very warm greetings from Switzerland, and I hope to see you next time at your construction site or in your office. It's my great pleasure today to take you to a tunnel construction site where interesting things are going on. So be curious and come with me.
Hello, everybody, also from my side. After this very inspiring video, we go now into the specific components. Okay, TSP 603 wireless. You have seen in the video already some of the components, and I'd like to introduce you also to the components a little bit more detail. You see a first sketch here, how the system is consisting of. We have the at least 4 receivers. We have little transceiver boxes to be attached to the receivers, and we have a tough pad, which is a simple tablet PC, and we have this wireless trigger box, as you can see here. That is to be attached to, in a normal way, to the explosive charges in the boreholes, but also it can be attached to an so-called impact source, which we come to later. So the wireless transceiver, as you can see, that little device over here is to be attached via this cable to the receiver. You have seen that in the movie. And with a closer look to it, you see it consists of 2 Wi-Fi antennas. So we are using the Wi-Fi system, either of the construction site itself, or we build up our own network. We have battery, Wi-Fi, and device status LEDs showing us at every time the status of the device, and we have a power switch. On the side, we have a USB-C type charger and power supply socket with which you can easily charge the battery inside, or you can even attach a power bank, so an external power supply to it in case the internal battery will be drained off. You can also attach to that a little pen drive in case the wireless system fails and the shot cannot be, or the data of the shot cannot be transferred. You easily attach here a USB drive and the data will be automatically loaded to this pen drive. You see the specs here in an overview on power supply. This power supply inside the transceiver also powers the receiver itself. As you know, we are using an active accelerometer inside the receiver. So the power for that comes also from the transceiver here. We have an integrated CPU, a processor in that device here. And this is, of course, with the highest precision of time synchronization of all transceiver. This is the biggest challenge of the whole wireless system, that we have the precise trigger moment, which comes from the trigger box, which is picked up from the trigger box and sent immediately to all the transceiver devices, and that we have at the same time, in terms of microsecond precision, the trigger time to all receivers. In a common way, that's a 24-bit AD signal conversion, and that will be then transferred to the tablet PC, which is also equipped with Wi-Fi. So the new trigger box, as you see here, it consists of very similar components as we have seen with the transceiver. We have, again, these 3 LEDs, battery status, Wi-Fi status, device status. We have the power switch, and we have 2 Wi-Fi antennas, and we have the USB-C charger and power supply socket on the side. What you see on the right-hand side here, this is what you already know from the existing TSP trigger box. We have the trigger switch where you can attach a hammer or any other kind of source, and we have here the socket where the cable to the blaster machine is attached to. And we have here the sockets for the instant detonator. So we're using detonator inside a borehole, or using non-electric detonators using the wire work trigger functionality over here. So that is the same. Despite this, we have the same housing. So the same housing we could keep here, and we have now also on that side here the whole wireless solution. Again, there's this own power supply inside a battery, which also feeds the little current which we need for the wire work trigger mechanism. We have this integrated processor inside here, and we support all kinds of trigger modes as usual, especially for blasting, but also for using a sledgehammer or the new impact hammer. Wi-Fi transfer, as you see here from the components, is also given then. So all the trigger signal is sent to the transceivers, and then from there to the PC. So how does the new receiver looks like? So you have seen that in the movie as well. The whole receiver looks similar, but is different, as you see from that piece here. The good thing is it only weighs 2.7 kilograms. All what you see on that figure here is 2.7 kilograms only. So including the protection tube, the receiver inside the dowel, and even the installation tool. And that is a plus 60% weight reduction compared to the existing system. If you go a little bit into the single components, you see the protection tube is now consisting of just one piece. That is a good thing. So you have less operation or assembly time in the tunnel. We have a little plug cone at the end, which plugs the borehole, mouth, and the whole thing is only 140 centimeters long. It's one piece, but one longer piece. So as you see from that, we have reduced the receiver size in length to 1.5 meters actually, as you see here how the receiver looks like. It's also one piece as a rod. It's very, very light. What you see here in the middle part is consisting of a carbon rod, and we have used special aluminum for the left and right end sides here. What is also new is that beside the accelerometer picking up the seismic waves, we have added an additional sensor which is picking up the spatial position of the receiver inside the borehole. We come to that later on. The hole is 150 centimeters long, so in future we just need even for boreholes, if you're still working with boreholes using explosive, we just need 150 centimeters long boreholes for receivers and boreholes, so it's just one length. What is also a little bit different is the TSP dowel. The whole concept is what we kept. So we have a dowel and we have the size-bound bag, as you have seen from the movie. What is different here with that dowel is that this dowel is now having a thread. So we screw the dowel on the protection tube. That gives us also a little bit more safety and gives us also a little bit more water tightness in that sense, that if water is inside the borehole, it cannot drop into the protection tube. We have also the improved installation tool. As you know from the past, installation tool was quite tricky and very heavy, and we have reduced that to a very simple installation tool, as you see here, which is also very light and easy to handle, as you have seen in the movie. So Joseph is now taking over.
So as Thomas mentioned before, open my webcam, sorry. As Thomas mentioned before, so we have included now a new sensor in the receiver. This is an integrated high performance e-compass. And this is an ultra compact sensor, as you can see here in this picture in the rule. So it is installed inside the sensor head, and it will make automatic measurement of these angles, the position of the sensor inside the borehole. So we mean the vertical, twist, and horizontal angle. So when we mention these angles, you know very well, but let's show you very shortly. So we are measuring now, so automatically the deviation of this tunnel with respect to this plane now in the horizontal. We have the vertical also angle. Okay, you know that we use the Swiss level to measure this, and also we can measure now automatically what we call the twist angle. As Thomas mentioned, data acquisition now is in a very easy way. We have a very light weight system, so autonomous is very fast assembling or mountable in the boreholes, reliable, accurate, and we have a long battery lifetime. So it means for the entire system, we have a weight reduction of 50%. It's also easy to use in the software. I'm going to show you now that in a nice video we have prepared.
Now we are in the software. Amberg TSP is acquisition. And first we will go to the home page. Now we go to settings. We have Wi-Fi devices. And here you can see all 5 devices. They are still not connected to the tablet. And now we are going to start each of these devices. You see, and turn it on, each of them one by one. And since we have already established a Wi-Fi access point between the tablet and the devices, you see appears already one on the tablet. It has been recognized. It's take now a little bit because they are booting the processors, each of them. We will see the next one is appearing. We see the status of the Wi-Fi, the status of the battery. Now we have all of them connected. We go now to the home page again. And now we go into one project. I select any campaign for this demonstration. And you will see now we are in the acquisition wizard as you already know it. There is one new feature in this one that you are looking at now is this geometry editor. I tell you this will be the next topic in our next user webinar. And you see now we are in hardware setup and check. You see all the devices are connected, are recognized by the tablet. This is the indication in the lower pane of each of these transceivers, as you can see here. Showing also their position with respect to the tunnel phase. And we have only one connected to a receiver. It's this one that appears everything in green, everything is right. We use the same coloring as in the existing acquisition software. When you see, just see this is the transceiver, number 1, connected to a receiver. We have now the receiver placed between the desktop and the floor. You see with some angles, so more or less obliquely, so 30 degrees. Okay, now we go to the software again. We will want to show you this new feature, and it's the angles that are streamed now by this sensor, this e-compass. You see the vertical angle is about minus 32 because it's pointing downwards. And we see also the twist and the horizontal angles. Now you see the vertical has changed to almost 3 degrees. And now I will move it downwards. We go to minus values. I move it upwards, go into positive values, come back to horizontal. Now I move the twist angle. You see now the twist angle is changing from positive to negative values. And finally, I will move the horizontal angle, which is the azimuth of this receiver spatially. Now we are in the ready for recording status. Now we simulate this with the trigger switch. And now you can see the data we have acquired. Of course, we have in 3 of the transceivers, we have only electronic noise, but in the one in which we have a receiver installed, now we can see the traces.
So now I'm back here. I'm taking over, explaining you now the next topic, which is about TSP impact. TSP impact is using an impact hammer, as you can see from that sketch here. For example, in a TBM environment, as you have seen from the movie, the hammer was installed on a console on the left-hand side. In that case, it can be also the right-hand side, but it's on the side wall at a position where it good fits into the TBM housing. Even if there is a shield around, you have seen that in the movie, there's a little gap which can be opened for this double sheet machine, where you can then install the hammer and let the hammer strike every time when a stroke of the TBM is finished. That is given here, so you can use 4 or even 6 receivers. This is very lightweight, as you see. You have seen that in the movie, how the mounting of the receivers is. You don't need anything else. You just install the receivers. The hammer, once it is installed, it's going on striking every time there is a little break with the TBM. You can use that as well. For example, install the hammer to, for example, a drill jumbo, or any kind of, let's say, vehicle inside the tunnel. So it can be also a little vehicle where you install the hammer at the front and move then the vehicle stepwise, as we know from using blasting in boreholes. We can use that also in this kind of conventional tunneling work. That will then, of course, replace the drilling of the boreholes, providing all the explosives. For blasting, you don't need a blasting master. You don't need any kind of blasting material. You just provide this kind of vehicle, which is then dedicated for this kind of job. We have seen that figure already here. So this kind of impact source is then hitting on the sidewall. It can also hit on the face. In case you want to have additional short lines, you can even use that at the face itself. You see a little sketch of that here. It's actually a photo which is introducing the hammer itself. So we have the hammer and the base of the hammer over here. There's a little control unit beside that. And in case you use an independent vehicle, so not a TBM, you need, of course, an air compressor providing you enough pressurized air. You see here also a compressed air reservoir, which you usually don't need. It's just in cases if you cannot provide constantly the requested pressure of air. That is the hammer, and when it is in positioned in front of the sidewall. And we have also provided here a little video. So it's pre-stressing. First of all, now you should see the hammer installed at a little mini excavator. It's not visible. Okay, now you should see that. The hammer installed upside down at a little mini excavator. So you see the hammer can be used in any kind of position, whether it is inclined, whether it is upside down, whether it should hit to the ground or it should hit to the ceiling. It always works like this. So we have just the air compressor connection here and the installation of the electric cable over here, and that's it, what you need for that hammer. So I'm starting in the next little sequence of strike. See how fast work on this concrete layer here. So every few seconds you can release strikes and give you then many strikes on the same position. And that is actually wanted. And this is what we later do then in the processing when we have stacking of data. But that is another topic which we already explained to you, but which we maybe will repeat also in one of the next seminars. Okay, you see now a little bit about specs. So the hammer and the base, as I said, so the good thing is that both can be separated from each other by just releasing those 4 screws on both sides. That's quickly done. So each part, the hammer itself and the base here, consists of or is weighing 28 kilograms. So that is, of course, it's heavy, but it's not that heavy that nobody can carry it. But you just need to install it once to a vehicle or to a platform console inside the TBM, and then it's done. You see, we can have more than 50 strikes per minute. The only thing you need as a supply is 7 bar of compressed air. That is always given, for example, in a TBM, in a conventional heading, as I said, with a forklift or with a single dedicated vehicle. You can use a separate a compressor line. And we also need mains power supply, or if that is not given at all, then we can also use a 24-volt battery beside the hammer somewhere. Total dimensions, as you have seen also from the video, it's not really big, so it can be, and that is also a good thing. It's quite small. It can be installed in normal sized TBMs under normal conditions. Good. The next video here is giving us a short sequence of shots done, and if you listen to this in the background, you hear the strikes, and you can then also see here what happens inside the acquisition. So it was ready for recording, waiting for devices. So we have here both transceivers and the trigger box.
That was a nice shot.
Trigger box, and then one guy is then releasing the strikes one after each other. Okay, that is a little overview we have done from our experience using explosives, using impact hammer, the new one here, and using a sledgehammer, as you can see from the picture here. You can use the sledgehammer. Some of our customers already do, having a little hammer switch at the handle of the hammer, and then connect it to the trigger switch socket at our trigger box, and then you can easily get also the strike from a manual hammer. As you see, how the energy is that, of course, with explosive, comparable maybe to 50 grams, we have this is a comparison taking almost at the same construction site, so with the same geology. So this comparison is valid. What you see is that with the explosive, we have about 3 times higher energy entry, of course, into the ground compared to impact hammer. But if you know that we can stack all the data from the different strikes at the same position, if you do 10 strikes at the same position, you can add on the energy and enhance also then the signal to noise ratio, which also gives us then a much better signal quality compared to other sources. Signal frequency, as you see, is almost the same. That is a good thing compared to explosives, whereas with a sledgehammer we are a little bit lower. And if you look at the prediction range ahead of the phase, as we usually say for explosives, 150 to 170 meters, which is with the impact hammer some 80 to 120 meters, which is of course less. That is what we knew just from the beginning, but which is, as we think, quite good enough, especially if you apply the striking of this impact hammer continuously during your tunneling work. With the sledgehammer, we have a much less prediction range. It's some 30 to 50 meters according to our experience. As I said, this is data from almost the same geology in order to compare this best. So we come to an end of our webinar. We have introduced the next generation internal seismics to you. This adaptation of hardware and software is what we think a further step to the digital transformation for the tunneling construction industry. We have a smoother integration into the excavation work cycle. If you see if you have looked the video, you see how easy it was to operate inside the tunnel. There is really more comfort for the operators and not only from the weight point of view, but also from the assembly point of view and how to get rid of all the cables and how to operate the whole system once it is switched on. So everything is faster, easier inside the tunnel, and as I said again, tremendous weight reduction, which is of course also a very good plus point over here. Good. If there is any question, you can drop us a mail. For sure, there are questions around, I guess. So send us an email to support.geophysics@amberg.ch. We are very, very happy to receive your emails, and we would be even happier to reply to them. And of course, I think there are many more questions around. This is just giving you a first overview. Joseph said it's the first time that we presented this, especially to our customers, but also to our partners here, which are online. So thanks for joining us. And thank you for attending. And we hope to see you soon again on your construction site with your next project in your premises, locally, in your country. And this is what we are all very much looking forward to. And stay healthy and stay safe. Goodbye, everybody.
Goodbye.